retired university professor, Dr. Nigel Bunce, who is an environmental chemist and toxicologist. In fact, he has retired, but he's still around. I see him walking the campus every day. So we used this textbook. It's quite a good textbook, although I would have to say it wasn't as accessible for first-year students as some of the university level chemistry textbooks. Sorry. Okay, next slide. So how did we try to engage these environmental science students? Well, we did it in a number of ways. In terms of the textbook, we tried to use environmental chemistry problem sets. So these are standard problems that you would see in any chemistry textbook at the first year level, but we're trying to use environmental issues. So for stoichiometry, we're looking at the production of acid mine drainage, right? So calculate the maximum yield of sulfuric acid produced from 125 tons of pilot. That's just a theoretical yield calculation, but it's a theoretical yield calculation that allows us to talk a little bit about acid mine drainage waters. I'm not going to solve these. I'm just not going to do that on your own. Under thermochemistry, calculate them. This is a very simple calculation. Calculate the mass of methane that must be burned to heat a typical house in southern Ontario on a winter day when the total heat requirement is 6.7 times 10 to the fifth kilojoules. Very, very simple little math problem there. In that course, we did talk about photochemistry, which is normally not taught at the first year level in most chemistry courses. And in this particular example, we're trying to relate to the whole issue of ozone depletion, looking at CFCs and how that chlorine gets cleaved from the CFCs. And this question is quite a nice question because what it shows students is that you cannot cleave that chlorine atom in the troposphere, but you can cleave it in the stratosphere. And this allows us to begin to talk about ozone depletion and CFCs. Next slide. I just pulled a few examples out. There are lots of them in the textbook. I really like this kinetics example. This is just a first order rate equation or rate calculation, but we're using pesticide degradation as the example here rather than some other compound that students have no real connection to. And again, it allows us to then talk about pesticides and fate and behavior in the environment. One of the critical aspects of pesticides in the environment is how quickly they degrade, and also how easily and quickly they are absorbed or not absorbed. So this allows us to talk a little bit about degradation. And then this free energy calculation allowed us to look at equilibrium versus steady state. If you do this calculation, calculate the equilibrium constant for this reaction, oxygen going to ozone, and estimate the ozone content in the stratosphere. If you actually do that calculation, you come up with a very, very tiny ozone concentration, and then you can say to students, obviously, there's something else adding to the ozone content in the stratosphere, and that something else obviously is sunlight, which is a driving force for ozone production in the stratosphere, and so you can talk about steady state concentrations versus equilibrium concentration. So this is one of the ways we try to engage students in this whole area of environmental chemistry. Next slide. The other way then was to have specific units developed about specific environmental problems and or environmental issues, and the issues that we talked about in that 2-semester course were greenhouse gases and climate change. We did quite a lengthy unit on photochemical smog and ground level ozone. We also talked about water issues, primarily water quality issues, and in that unit we talked about water hardness and water softening to begin with, which led us into talking about a bit about water treatment. This is the one part of that course that I always felt was rather poorly done, and that was the lab portion. At the University of Bolton, I think this is the case for most universities, first year chemistry, the lab and the lecture part are really run sort of independently. I had virtually nothing to do with I taught this course, but I had virtually nothing to do with the labs. There's a full-time first-year lab coordinator who coordinates the labs, coordinates the huge team of demonstrators and TAs, who make sure all of the materials are prepared every week. And so when this course was reworked to increase the environmental content, the only lab that they changed in that whole course was to introduce a water hardness lab. All the rest of the labs were exactly the same labs as the regular first-year course took. So that was difficult for students because they were getting all this information about environmental issues in the lecture, but they weren't really getting anything in the lab. That's partly because it's difficult to come up with good environmental chemistry labs that can be done in 2 hours. That's not an easy thing. So I'm not criticizing, I'm just saying that it just didn't really line up with the course terribly well. But they did do a water hardness by titration and stamping EPH, which is a classic first-year experiment. We talked a little bit about biological oxygen demand, and we talked a little bit about sewage treatment in the water unit, and we talked about acid mine drainage. So that's another way in which we try to engage students, because many of the students from high school were familiar with many of these topics, so we could try and integrate that into teaching chemistry. I just wanted to add this last thing, though, because I think, and Jason is very kind talking about my enthusiasm, but I think this is where I often was able to engage with students about environmental chemistry. Because I have a background in applied chemistry, so I'm soil and water chemistry, I have many stories. I put quotation marks around my stories because over the years these stories are not really based on truth anymore. They've been kind of they've grown into something that I'm not even sure what the real story is anymore. But it didn't matter, because what mattered is I was able to tell students stories, real life stories, that could connect them to chemistry. In fact, this semester I'm actually teaching a second-year course in soil science. I'm not sure how many people have ever taken soil science, but soil science is sort of a fundamentals course as well. We do a little bit on soil classification, then we do a little bit on soil physics, and then we do a little bit on soil chemistry, and we do a little bit of soil biology. And I spend a lot of time on the soil chemistry part, because unfortunately for the students, that's my background. And I can tell that they're getting something more out of what I'm saying if I can explain to them why it is important that they understand the equilibrium constants. If I can give them a real-world example of why that's important. So over the years, I found that these stories, which I have stolen from colleagues and picked up from research projects I've done, are always extremely useful. So just to give you a couple of examples of stories that I tell, I often, when we get to the unit on solubility, I often tell the story of why the walls of the Welland Canal are crumbling. I'm not sure if people are familiar with this, but they've, over the years, had some problems with the Welland Canal walls beginning to deteriorate. So it's sort of the material behind the concrete canal. And the reason for that, should I cut the story? The reason for that is because one of the minerals that is found is quite prevalent in the sort of Welland area is gypsum, calcium sulfate. And so I asked the students, if you have gypsum, if you have calcium sulfate, and you know the content of calcium and sulfate in the waters that are flowing through the Welland Canal, those waters are coming from the Great Lakes, so you can actually figure out what the average calcium and the average sulfate content is. Can you calculate whether or not that gypsum is in equilibrium with that